Hi, everyone. So before I start, I'm just going to quickly put this video because I think it really shows how we all been working so hard to present here at OffensiveCon. I really want to thank you, OffensiveCon, for having me again. I've attended 3 conferences. I like it. I'll come back. But basically, when we build stuff or when we try to destroy stuff, we have lots of problems. And I like this video. You try to solve one problem, you have another one, and your manager is behind you. Right. So that's what we do, right? So I'm Cedric. I'm part of the exploit development group at NCC Group, and my goal, my job, day-to-day job, is to write exploit for existing vulnerabilities that are patched, so our pen test team can use this exploit and demonstrate that if you don't patch, it's bad, basically. The exploit we write are just more than proof of concept in that they have to work as much as possible and for all the versions that we can, if possible. The research I'm going to be presenting today has been done with Aaron Adams, who is not going to be here, but we work in the same team. So the presentation I'm going to do today is about a Windows kernel vulnerability in a component called KTM, which stands for Kernel Transaction Manager. It actually was found by Kaspersky and Boris, and who presented the research on Blu-ray earlier today, and Igor. And they found it exploited in the wild, and they published a blog post about how roughly they found it, and at least what were some explanation about the bug. It was exploited in the wild at the end of 2018, and we were interested in this vulnerability, and we started researching into this vulnerability in 2019, early 19, so a few months after. And we never got access to the actual exploit or a lot of detail. We only had access to this Kaspersky blog that gave us a few hints about the bug. The first one was that this was a race condition in this new component that we didn't know at that time, KTM. It was exploitable in the browser sandbox because it's allowed to access KTM from the most browser sandbox, contrary to Win32k, for instance. It was working on Windows 10, and there was a few hints to trigger the race. The presentation I'm going to do today is very similar to the one that was presented at POC at the end of last year by Aaron there. Just a few things when you start a new research, just doing a little bit research on Google to see what was in KTM. Actually, it wasn't a component that has been targeted a lot, because in the last 10 years, only 4 CVEs, and most of them are not actually exploitable bugs, just denial of service or memory disclosure bug found by Joru. And so among the 2018 one is the actual Kaspersky's blog that we took as a reference, CVE-2018-8611. And there was another article about KTM, which actually was last year, about ways to evade AVs using KTM. So this is basically the thing I've read probably 200 times, but I mean really, among the few weeks and months I've been working on this exploit. And basically, at first you read it and you're like, oh yeah, that looks really, I'm not going to go over it because I'm going to go into detail, but you can see there are a few links to some functions that are called transactions, enlistment, resource manager, objects. And basically, this is for me, when I read this blog post, I'm like, okay, so actually, should be easy, right? So a few tooling if you're interested to see what we use. So basically, when you start, we want to exploit an existing vulnerability. The best method is to use Halbronn method, which is use bindiff. So in our case, we use Diaphora, mainly because we want to have the decompiler, and you get this list of functions. The one that you can see, TM recover, resource manager, 38 block changes. This is the one we're interested in, and basically it looks like 4 different pages like this. Okay, so this is definitely not an integer overflow before malloc with just a check that is not checking the length of an allocation, right? So, and even if you have the decompiler, you still have pointers, you don't know what's going on. So now we need to analyze to understand what is KTM, okay? Because we can't just say it's an integer overflow. We know it's a race condition, but for now, we don't have any information about the bug. So we're gonna go over KTM, see how a little bit of internals to understand the patch, how we triggered the bug, how we basically managed to get an arbitrary read-write primitive, and how we escalated privileges. So what is KTM? So KTM is very specific to Windows. So basically, you look at the MSDN, the KTM portal, and you get something like this with like a list of enumeration function structures that you can call from userland or also from kernel, actually. There are both APIs. And basically, KTM actually was added in 2006. And basically, it's a component to deal with transactions, similarly to what you would think when you deal with a database with transactions, SQL database, where you want to have different requests and you want to make sure the transaction operations you do will, if something fails among the different transactions, you will always have a consistent state and it will never be corrupted and you can always revert to a previous state that is sane, even if you lose the latest changes. So this is actually in the Windows kernel. So they have this kernel transaction manager. And so it's been in Windows since Vista. And it was in TOS kernel first, and now it's in tm.sys specific. It's actually in the kernel, but it's also used by two other components in the kernel called the transaction registry and the transactional NTFH, which, as you can imagine, used KTM to implement it for the file system or the registry. And it's also available from userland to, so from userland you can create transaction and it's going to use the KTM from the kernel. So after browsing the MSDN pages, also a lot of times, and playing with it by writing some C code just to interact with it, we understood that there were 4 different objects that were really important for talking with KTM. They're all reference counted, and basically you have the transaction manager, you have the resource manager, transaction, and the enlistment. The transaction manager is the one that allows you to manage the logs that will allow you to revert to a previous state. The resource manager is the one that manages the specific resource that you want to deal with for a transaction. Then you have the transaction object, which you create to say this will be the whole work, the whole actions. I want to be part of the same transaction. And then you have the enlistment, which is basically the link between the resource and the transaction that will enlist to a specific task. And this is basically how it works. You have 4 different functions that you can call from userland. So create transaction manager, create resource manager, then create transaction, the one at the bottom, and then create enlistment to enlist to a specific transaction for a particular work. So just I won't detail all the arguments because it's going to be boring, but I want just to highlight a few arguments that are interesting for the bug from our exploitation point of view later. So for now, probably you won't understand why I'm talking about this argument, but just for your information. So when you create a transaction manager, you can pass a log file name, and it's either you pass an actual file name that will be used on the file system to save the transaction on persistent memory, or you pass null and you get a volatile transaction manager. So we would say, why do you want to have a volatile transaction? Actually, I don't really know, but from an exploitation point of view, because there is no log, so it's you can't roll back really. But from an exploitation point of view, it's interesting because there is a limit on the actual log, and so being able to create volatile transaction manager is useful from an exploitation point of view. So we create a transaction manager. It creates a KTM object. Most of the fields are not relevant for us. When you create a resource manager to handle the resource, you can pass a description, which is basically a name for the resource manager that will be associated with this resource manager. or you can pass null to avoid creating a name. And the resource manager has a few fields that are interesting for us. So you can see the description at the bottom. You can see the transaction manager pointer that points to the transaction manager object. And then at the top, you can see the state or the flag of the actual resource manager. And there is a mutex, which basically dictates if you can access and read the description, or if you can browse the enlistment list, which is pointed by the enlistment head, which we'll see the list of enlistment. So you need to log this mutex to be able to browse this list or access this description. And then you have lots of fields that are related to notification. And it's because actually there is a queue of notification that can be triggered when certain events happened. And basically, we'll see later that actually this notification, we can read it from username, which can be useful. That's what I said. So then the transaction. So the transaction doesn't have really important arguments because it's just an opaque object that tells you this is part of the same transaction, but it doesn't. Nothing is associated with the transaction in itself. Just a piece of work to be done. And then you have the enlistment, which is basically to enlist to a specific transaction that's going to associate the transaction to the actual resource. So the enlistment is very important for us because as we will see, the bug actually allows us to trigger use after free in the enlistment. So knowing the actual layout of the object is very important. But basically, we can see we can pass the handle for the resource manager and the transaction. So the layout of the object is this. So it has different states for the actual enlistment. The notification mask dictates what are the different notifications that will trigger an event when the enlistment changes state. And then you have the next same RM, which is the linked list of all the enlistment associated with the same resource manager. So I can understand it's a little bit messy, but I'll show you a figure in a second. For the actual flags, the actual flags that are interesting, so when we were reversing, this is how we documented the flags, but the two that are interesting for us are finalize, because the finalization of an enlistment dictates when the enlistment has finished doing its work, and basically the enlistment can be freed. And the second flag that is important for us as well is the superior flag, because in the KTM world, they have this concept of actually distributed transaction between different hosts, and you can have a superior resource manager and superior enlistment that actually is the one that kind of orchestrates the other thing. But in our case, we don't really care. So that's something we can kind of ignore for now when we reverse engineer. So how do we free an enlistment? So enlistment are reference counted. By reversing, we find this function tmp finalize enlistment that we can see it lower the ref count, and we can see that it does it when it actually moves from a prepared state to a committed state. And so we can see that from userland, we can call commit complete to trigger the finalization of an enlistment. And if there is no reference on the actual object, which means we need to close the actual handle we got in the first place from creating the enlistment, then the actual enlistment will be freed. And if there are other references in the kernel, once these references are gone, the actual enlistment is freed. So this is basically a summary. If you don't get the whole thing before, this is a summary to be able to follow the remaining part. So we have the actual transaction manager, which is the first object we create. We have the resource manager, which has an enlistment head, which is a linked list of different enlistments that are associated to either one or several transactions. But this linked list of enlistment is actually important to understand the bug. The transaction and enlistment can move from different states. And by reversing, we found that they can move from pre-preparing to committed. And there is a relation between the change of state for the enlistment and the transaction. Basically, what happens is if a transaction has several enlistments associated with it, all the enlistment needs to sync to a specific state, so the actual transaction can move to this same state. And it was actually very important because since there isn't much research on KTM, we actually had to define objects to the specific state so we could actually trigger the bug in the first place. So the last thing about KTM is notification. So there is an API called Get Notification Resource Manager that you can call from userland that allows you to get notified when specific enlistments change state. And we'll see why it can be useful. But basically, it's on a first in, first out basis, and you can follow that from userland. And you can even associate which enlistment had the notification by the structure that is returned from userland, from kernel, sorry, to userland. The last concept that we need to understand for KTM is the concept of recovery. So if a transaction fails or powers down, you restart your computer, and now you want to recover to a sane state, you can basically call recover resource manager, and it's going to try to go over all the different enlistments associated with the different transactions and try to see if it can recover to a sane state. And the way it does that is that it sends a notification to the different workers to synchronize them so they can decide what to do to fix the transaction. Okay, so understanding the CVE. So, okay, now we have a better understanding of KTM. So we started doing actually a better reversing. So we had this, we actually used a lot X-rays for this research, very useful. And if you actually start documenting all the different objects from your understanding KTM, K-Resource Manager, you end up having something that is a lot more readable. So maybe it's hard to read, but basically on the left you have the vulnerable version and on the right the patch one. And so in red is the code that has been removed. And basically the code that has been removed is the fact that it's checking an enlistment flag to check if it's finalized. And if it's finalized, it's going to set a Boolean to 1. And then it goes outside of this if-else loop. And there is another if loop that checks on this flag. And if this flag is set, then it's going to basically start from the head of the list instead of going into the next pointer, the flink pointer, which is just below. So basically what has been done is this thing has been removed, and instead on the right, there is a more code, which is confusing, but you can forget all the line except the last one. The last one says, okay, just give me the head of the list. So basically what happens is they remove the check on the finalized state and the Boolean, and they just assume, let's start from the head always. And there is no if-else. And so there is an additional code that actually checks on the transaction manager, but for us it's just like an optimization to exit the loop as soon as possible. Okay, so we have an understanding a little bit of the loop. This is probably the hardest part to understand because it's a lot of code and probably not that useful, but just take it as I'm talking more than just reading the whole code. This is the recover resource manager loop that basically is going to loop on the list of enlistment that we saw here. There is a list of enlistment pointed by the enlistment head, and it's going to go over each enlistment to see if it can notify them. And the way it does that, first, it's going to check if it's the enlistment head, meaning it's done with the list. It's going to just exit the loop. It's done. The function has done its work. The second thing it's going to do is going to check if the enlistment has been finalized already. Because if it's been finalized, no need to actually send a notification. So we're just going to skip it and continue to the flink. The next thing is it's going to bump the enlistment ref count. And this is so the enlistment cannot be freed, and we have a lock on the enlistment. Then the thing is, the ref count prevents the free later when we send a notification. Then there is an if to check if the enlistment is notifiable. So the enlistment is notifiable means we can send a notification later, and the thing it does is at the end of this if, is basically unset the notifiable flag, saying what it means is that if it wasn't notifiable in the first place, it will notify, but it will also never notify it again because the flag is unset. Then it also set this boolean to actually send a notification, and that will dictate that it actually calls this TMP set notification resource manager that will send a notification. But before it sends its notification, it's going to basically unlock the resource manager mutex. And it's a little bit similar to the race condition we saw earlier this morning on the Linux kernel. It's basically releasing a mutex before calling another function, and it's bad. What happens is that releasing the mutex allows the notification to actually finalize the enlistment, and potentially it can lead to deletion of the object if the ref count goes to 0. So we saw earlier that the ref count will not be 0 because we acquired the mutex on the enlistment to prevent that. But what happens is there is a check or the actual enlistment flag just after sending the notification to say, is the enlistment finalized? And basically, they are exactly trying to prevent the use after free. But what happens is that the code that is just after actually is prone to a race condition, because what happens is that it's possible to congest the mutex and make it that the actual free of the object happens while we are congested here, after the check of the finalize has been done. And so what happens is that even though we failed to detect that it was finalized in between, and then we actually are going to access a flink pointer, part of a freed object. So what happens is that the function is basically going over all these enlistments and is trying to make sure it notifies the enlistments that are not yet finalized and detect if the enlistment is finalized, and they are failing to do so. So, okay, so we have a better understanding of the vulnerability. How do we trigger this bug? So our approach has been to trigger a fake race, and it was mainly because back in the day, here I'm just describing my understanding of the bug because I've done the exploit for it, but back in the day, I think that while we're looking at this loop, we actually don't have this understanding, and I want to make sure we actually understand the problem. And so what we did, basically, is we patched the k wait for single object to be just a jump to loop forever while we are debugging. And in the meantime, we forced the enlistment to be freed, and we tried to confirm that when we were resuming the thread by unpatching in WinDBG, we would actually trigger a use after free. So how do we actually know which enlistment to free? So initially, our approach was to basically free all the enlistments, but after some thought, we thought that if we try to win a race, we may want to try several times. So we wanted to basically have a way to just free the one we want to target. And so our idea was to actually use the get notification resource manager to basically count the notifications that were received by the different enlistments and find the actual last enlistment that was touched by the loop, so we can free the last one. And actually, that works really well. We are able just to know exactly what enlistment has been touched by the loop and just free this one and trigger a use after free. So we confirmed with the driver verifier or just with the debugger that the bug was real. And if we're able to win the race effectively, it would work. So what would happen is that we would, the loop would fail to detect that the enlistment has been freed and finalized, and it would just access freed memory. So how do we actually win the race? And that's the part that actually took us some time. And maybe people who've done Windows kernel exploitation and race condition stuff would have done it right away. It wasn't our case, so it was actually hinted as well by the Kaspersky blog, even though it wasn't really obvious for us for quite some time. But basically, it's possible to suspend the thread in the loop and to effectively make it stuck at the exact time we're interested in. And the reason is because when you actually call the suspend function to actually suspend a thread, it will be more likely that it will be block on natural points like waiting for a lock, which is exactly the problem here, is that you can have a wait for a single object just after we win the race. And so the idea is to congest the resource manager mutex in order to increase the likelihood of suspending the thread at the right place by calling a function, a syscall from userland to query the resource manager information. And if we actually are able to suspend it at the right place, we actually have all the time we want in the world to actually win the race, because the thread is stuck exactly where we want, and it's actually doing the same thing as we were doing in the debugger, and we can just do what we want and just even go have a coffee and come back, hit enter, and we win the race. And the cool thing as well is that if when we suspended the thread, it's not at the right spot, what happens is we will not win the race, no use after free will happen, and we basically try again. So it's quite nice and reliable. So we can keep trying. So just have a few animations to show you how it works, because there are different threads. So we're on this loop, TM recover resource manager. It's passing all this enlistment list, and basically on behalf of the recovery thread. And what happens is, at the beginning of the function, it's going to log this mutex. It's going to test if the current enlistment we're parsing in this list is finalized and notifiable. And it's going to start queuing notification. So it starts queuing notification, and just before doing that, it's going to relog the mutex. Just after queuing notification, it's going to relog the mutex. And what happens in the meantime, we have a congestion thread that will keep spamming anti-query information resource manager to say, give me your name, give me your resource manager name, and it will effectively keep locking the mutex to actually read the description. And in the meantime, we have a third thread, which is the suspend thread, that will basically start to suspend the recovery thread, which is stuck in the loop. And the idea is we want to suspend it at the right place. So it's going to say, OK, I want to suspend you. OK, suspend now, suspend now. And so there is a trick here that we can use, which I think has been used by the exploit in the wild, because they use this function as well. But basically, you can use anti-query thread information. And the idea of this function is to query information about a thread. And you can say, I want to know the last syscall that has been used by a thread. And this function only works if the thread is suspended. So if it's suspended, you will get a reply. But if it's not suspended, you'll get unsuccessful. So you can detect if it's suspended or not. So the suspend thread says, OK, try to suspend you. Now you're suspended. There are a few notifications queued in the meantime. And now the thread is suspended. So what happens is the thread is suspended while parsing a specific enlistment. And so now from userland, we can count the number of enlistments that has been notified by using the notification function, and determine which enlistment we want to free from userland. So we can free this enlistment and then resume the recovery thread. And what happens is if the recovery thread was suspended at the right place, then we win the race, and we basically get a use after free. And if not, then we can try again. So so now we have the problem of how do we replace the object. We know everything is on the non-page pool. So pool is just for the term for the kernel heap. But basically, we know everything on the non-page pool, and we know the size of the enlistment. So non-page pool feng shui is the obvious approach. So at first, another thing that we didn't know, even though now we know it's been used by the actual in the wild exploit, is that there is a technique using named pipes, which actually is known. I think Alex Ionesco is the one who talked about it in 2014 back in the days. It's been recently used in a few blog posts, one from Blue Frost early this year. But basically, you can use named pipes. And it's a very good technique because it gives you a lot of control. And the idea is that a named pipe is like a pipe that you can send information to from one end to another and read and write. And the idea is that every time you write something on a named pipe, it's going to be allocated on the non-page pool, and it won't be freed until you read it from the other end. So you just have to allocate a named pipe and just start sending data on the named pipe, and you can allocate stuff on the non-page pool. And what is really cool is that you control the size because it depends on how much you write per write. And you control most of the data because that's the data you're supposed to write in a name pipe. The only thing is there is a data entry structure that dictates some information which you don't control, but it's small enough, and for us it didn't cause any problem. So how does it work? If you want to do some feng shui, you can open two name pipe A and B. Usual technique to avoid coalescing and being able to replay the chunk you free when you do use after free. So we allocate data on both chunks. We free data from pipe B. Sorry, we allocate chunks on both pipes. We free data on pipe B by reading all the data from pipe B, which create holes, and we use these holes to allocate all the enlistments that we were going to be targeting in our loop. And the idea is now our enlistments are in specific spot and bounded by other stuff that will never be freed. And so once we free the enlistment that we target for the use after free, we can just replace data with the name pipe technique, which I've just described, to replace the enlistment with a fake enlistment. So this is just to show the alignment between the name pipe and the enlistment. So here we failed, well, we succeeded for the exploit to replace the enlistment with a fake enlistment, which contains a next same RM flink pointer, which is pointing to something. So the thing I didn't explain here is delayed free list. So there is a concept in the Windows kernel, which is, I think, mostly for optimization, which is that when the chunks are freed, they are not actually freed right away. They are put into a delayed free list, which is a way to make them available when you want to reallocate chunks quickly. And it's been in Windows since Vista, but basically the idea is that when the 32 chunks are in this list and the list is full, then it's going to flush the list. It's going to actually free the list and free the 32 chunks. The thing is, for us, it doesn't really matter. And actually, the first exploit we got working didn't take into account that. The interesting thing behind it is that because we can trigger the race several times, we're in this loop. Even if we actually make it suspended on the right spot, and we actually fail to replace the object, but because of the delayed free list, when it's going to actually use it, it's going to use it from the one in the delayed free list, which hasn't been reused anyway. So it's going to use a stale pointer, which is valid, and it's going to just continue in the linked list. So it's just going to fail. We won the race. We just failed to use after free. But we can try again, and it works. So, but obviously, the good method is to actually free 32 chunks to free the list because it's a simple method and it just makes it faster. So how do we go from that to actually detect a race win? Because we are in New Zealand, we don't know when we win the race. The thing is, there is no SMAP. So that's very useful. The thing is, what we can do is we can use the fake, the first fake chunk that was replacing the enlistment object, which is in red, point to an enlistment in New Zealand, which will be touched by the loop at the next iteration, and make it that when it actually parses the enlistment, it's going to change something, and we can get this information from New Zealand because we can read this enlistment. So the thing is, we saw earlier that in the loop, the first thing it does, it checks if the enlistment is notifiable, and if it's the case, it just unset the flag. So we just make sure our enlistment in userland has this flag set, and it will be unset by the kernel, and we can detect it from userland. So here we detect we won the race. What we do next? The problem is that if we make it point to another enlistment, another, we can maybe queue 2,000, but at some point it's going to crash if we don't know where to point the enlistment. So the technique we used is basically to point the enlistment to itself. So it's going to basically be stuck on the same enlistment, which is our fake userland enlistment, until we actually decide to do something about it. And when we are ready, we can just change this fling pointer from userland and make it point to another series of enlistment that we want to do work for. So we name this enlistment the trap enlistment because it's trapped into the kernel. So, okay, so the next thing is how do we actually debug a race win? Because so there is using a debugger, using like the different printfs, and we decided to use another method just because we repetitively debugged it, and we found a technique which basically consists in using the superior flag. I said earlier the superior is used in the case where we don't care, but it's actually, there is code in this function that actually dictates different things if it's superior. And so what we can do, we can just set the superior flag if it's enlistment, and set a breakpoint in the enlistment case, in the superior case, and it will only trigger for our fake enlistment. So it doesn't slow down any race or whatever, and it will trigger once we won the race. So it's quite nice just a trick to debug. It's something to keep in mind where you're developing an exploit and repetitively trigger the exploit. So the next problem we had is how do we actually escape the loop? So the first thing to know is that if we actually escape the loop, we lose any primitive because the advantage is we're in this loop and we have some control, but once we exit the loop, we actually don't have anything. So we have to do everything previous before exiting the loop. But the thing is, even though we are thinking about, okay, we want to find this right primitive, it's actually good to think about how to escape, because we're going to repetitively execute the exploits, it's good to have a clean thing that exits properly, so you don't have to resume your VM or restart your VM all the time. So we're thinking about that in the background. And while we're trying to find a right primitive, we noticed that we were building some fake enlistment with right structures inside the enlistment, and we noticed that the enlistment that was touched by the kernel actually leaked some pointers into our fake enlistment, because the mutex of the enlistment, which is the K mutant here, gets two pointers get added to a linked list, and one points to a K thread, which is the current thread of running in kernel, and the other one points to the K resource manager, which is very cool, thanks to K wait for single object. And this actually technique could be applied to other bugs. I think it's quite generic, the fact that you can create a fake mutex that is touched by the kernel. But what is really cool about this technique is that this leak is that it leaks the K resource manager address, which is exactly what we need to exit the loop, because the test is if the fling pointer equals the address of the enlistment head in the K resource manager object. So now we can just escape the loop by setting the fling pointer to the head of the resource manager. So this is what it looks like now. So we have the escape enlistment on the right that points to the leaked K resource manager. And in between, we had our first trap enlistment, number 2, which allowed us to detect we won the race. And then for now we don't have it, but we want to have what we call limited right primitive, LWP, which basically is a series of enlistment that gives us some kind of right primitive. And then we have another trap enlistment that tells us that this right primitive has been done, and then we can again queue other enlistments, and so on. Okay, cool. So we can go into kernel, we can make it race, we can make it user after free, we can make it return to userland. Cool. But we haven't done anything for now. We don't have any right primitive, we don't have anything. So we're digging deep to find a right primitive. And lots of reversing, documenting stuff. We don't know where we're going. The cool thing, though, is that we're stuck into this function. So we know we have to find something in the function that are called inside this loop. And the one that looked the best was ke release mutex, initially because it has linked list that could be used for mirror writes, even though now, after Windows 7, so since Windows 8, there is safe unlinking, so we couldn't use them. But it looked interesting, and so we kept looking, and we actually found an arbitrary increment where here the interlocked add, we control the thread queue, we control current count, so we can make it an address that points in somewhere and increment it by 1. The thing that it's very complicated, because there are lots of functions that are being called. You need to actually define lots of constraints to not only trigger this increment, but also then to avoid crashing in other part of the code to actually make it triggerable several times. So I won't go into detail about that. It's too complicated to go in a presentation, but we'll post a series of blog posts about that. The cool thing is we can chain multiple increments, so we can increment an address several times, and we can actually build an arbitrary write primitive. The negative are that to actually increment it to a known value, we need to know the first value in the first place, because we are incrementing by 1, so we need to know the initial value. And there are some risk in dispatch level. And basically, what we have now is that we can trigger this series of increment primitive and make it finish by a trap enlistment, and we'll know that all the increments have been executed. So this is how it looks like in terms of all the structures we need to define. Obviously, I won't explain it all, but it's lots of constraints, and it depends on the OS, even though most of them are quite the same, which is lucky for us. But this is basically when we build all these constraints and we start our exploits. We just want to sure that when we touch it, it's not going to explode, because when we see that, it's likely to explode. Okay, so now we have an increment. The problem is we don't have an arbitrary read. So we can't read memory, we can't leak the address, we want to overwrite to get something else. So we want to build an arbitrary read primitive. The thing is we have a good understanding of KTM, not only because we did have to dig into all the API documentation because there was none before, also because we had to reverse engineer a lot because we had to find this right primitive. So the best choice for us was to actually use KTM to build a read primitive. And actually, we used a K-resource manager description. Because the thing is, this description can be, when we create a resource manager, we can create a resource manager that has a description which is null. So the pointer, the name pointer, and the length of the Unicode string will both be 0. And so we know the initial value. And that's exactly what we need for using our increments. We need to know the initial value. So we know they are 0. And we know the address of the resource manager because it was leaked in the initial leak. So we can actually overwrite the length and the name to build an arbitrary read primitive. And so the idea is we can use the syscall to read the description from userland, and after overwriting the pointer and the length, and we can repeat that because we knew the previous version we overwrote in the first place, so we can just rinse and repeat. So this gives us an arbitrary read primitive. So this is the updated diagram. The idea is that we initially had the use after free. We have the initial trap enlistment that allowed us to leak the address of the resource manager. From the address of the resource manager, we know the address of the description. We know that both values are 0. So we use the increments to increment the description field to the address we want to leak. And then we leak the address with the syscall I said before. And we can leak any value. So now we've done the leak. It finished with the trap enlistment. We can restore the previous value from the description once we're done with the leak. So now we have our arbitrary leak primitive working. Okay, so some people would say, that's cool, incrementing a 64-bit number, 2 to the power of 64, that's going to take a while, yes. And we had these questions at POC, so we added this information. But basically, how is it possible in practice to increase a value to the value you want in 2,000 writes? The idea is, just as an example, you have at address 1,000 hex, you have 8 bytes. It is your 64-bit value you want to overwrite. It's initially 0. You wanna make it 1, 2, 3, 4 hex, but you don't want to do 1, 2, 3, 4 hex increments. So what you do is you just increment it 34 times at address 1,000, and then you increment it 12 times at address 1,001, and then you've just reduced the amount of time. And you can do and so on. The only problem is that once you arrive to the latest byte, if you want to increment, for instance, 40 to 3f, which is lower, the most significant byte, the problem is while you're incrementing it, so if you increment it C1 time, it's going to reach FF, and then if you want to hit one more, or at least the amount that is needed to reach 3F, when you actually increment it from FF to 0, it's going to actually have a carry that is on the next byte, and you corrupt the adjacent memory, so that's bad. So the trick to avoid that is that what you can do is you can reset the previous value, the whole 64 bits to 0, and the way to do that is you set every byte to FF. So you start with the first byte, with the first technique, with the misaligned increments. You do it FF, 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 and once you reach the FF, full FF, what you do is you do an align increment on the 64-bit value, and basically it's going to overflow, but it's not going to overflow memory. It's just going to overflow the 64-bit value, but it doesn't matter, and you don't have any side effect. So effectively, you have one run to set everything to 0, and one run to set anything to the value you want, worst case. So it's 2 times 256 times 8, which is 2,000. OK, so we have an arbitrary read, we have an arbitrary write. So how do we get prevesc? This is standard technique, but basically we used the increment to replace our process token with the system token. So we basically use the increment to build an arbitrary read primitive. We leak the system token, and then we use the write primitive to override our e-process. The only thing is that because we are actually overwriting a pointer, the increment can actually make the pointer invalid. So potentially, if something reads the pointer while we're incrementing it, it can be SOD. So there is a risk of BSOD, for instance, if Task Manager or Process Explorer is actually accessing the linked list of eProcess while we're incrementing this thing. And it may happen. So our technique is data only. We didn't investigate bypassing CFG, even though we think the bug is quite powerful and it should be possible. We ported it from Vista to 10, both on 32-bit and 64-bit, and that was quite straightforward. The last thing I want to present is some bonus work on some work we found after we made our presentation. Basically, what happened is that it turns out Boris and Anton from Kaspersky, even though they published this amazing blog post, they actually published a series of slides explaining more that we hadn't seen before. But basically what happened is that actually describes some methodology of what they've used. And we actually didn't find it. And at that time, we were like, OK, we didn't find it. We found it by accident by looking for Win32k filtering search, but we couldn't find it by searching for the CVE or KTM. And so at that time, we're like, OK. Actually, at the end, it ended up being a happy story, at least for us, because the approach they took was different from ours. And this is what I want to talk about here. There are three things that I want to explain that are different, and that actually makes it very interesting for us. Is that the first thing for detecting if they won the race, it doesn't seem like they actually use the same system as trap enlistment, making the loop stuck temporarily, which was quite nice. They use some kind of mutex and even notification object in the kernel that makes it trapped temporarily inside some KE wait for single object, and they are able then to modify it from userland to restore it, and also to do a write primitive. So it's interesting because it's a different approach. And the other thing is it's actually more complicated than our method, because our method is just setting a flag and checking if the flag is unset, which was quite nice. And so their method actually also dictated what they use afterward, which is that they actually don't use an increment either. They actually use the write zero primitive, so I was, well, that's cool. They didn't even use the increment. And so they use the write zero in the same kind of path that we actually found the increment in, which is quite interesting. And so they have the capability to write zero to any address. And the only thing is there is a constraint that the least significant bit must already be 0 to avoid deadlock, but it works. And actually, in order to reach the write zero primitive and avoid crashing and everything, it's a lot simpler. They don't have to go that deeper instead of our increment, so that's nice. It's better. It's easier to exploit. The only thing we realized after by analyzing this powerful technique is that the only thing is it doesn't work on some case like Vista 64 because of some difference in the code, and also on Vista and 7x86 because of some different macro that is used in the Windows kernel that makes the primitive not working. Because the whole value needs to be 0 in the first place to actually write 0, so it doesn't work. And the other thing we initially thought it was actually writing 0 shouldn't be that powerful, because actually being able to increment looks better, right? Because we can increment to any value, whereas write 0 is just one value, right? But actually combining the write 0 to another trick, which is using the previous mode, the write 0 becomes a lot more powerful. And this technique was first documented by Targement in 2011, as far as I can tell. The idea is that you can override the k-thread previous mode field, and previous mode dictates if a syscall, if when a thread is running in the kernel, if the thread has been called from userland or if it's a kernel thread. And basically what it means is that in the kernel, some checks will be skipped if the thread is kernel and it doesn't come from userland. So if you are able to set your previous mode to 0, which actually dictates it's the kernel, 1 is the user, 0 is the kernel, or 0 is the kernel, and anything else is the user. So if we can override previous mode with 0, we can basically say, oh, now our thread is kernel, and we can just call NT-read virtual memory or NT-write virtual memory from userland, which are syscalls to read or write memory. But because it thinks we are kernel, we can read and write memory from the kernel. So it's really cool technique. So it looks really super powerful. The only thing is when we were trying to port this technique to see the advantages, we realized that actually it only works on 64-bit, just because the previous mode, the way it's implemented in 32-bit, it's different, and they basically don't rely on it really. They just every time the syscall is made, they're going to override the previous mode in the kernel using the CS register. So we can't actually override it and make it used by the kernel. It's supposed to be the first in the wild use of the previous mode, if I'm not mistaken. So that was cool to see it. So I have a quick demo. So as I said, the increment technique can crash if the thread, if the if the task manager decides to read the pointer we're incrementing while we're incrementing. But for now, we're just triggering the exploit. So we're gonna trigger the recovery of the resource manager, and we're gonna make this thread in the loop, and then we're gonna try to win the race by suspending the thread multiple times, trying to detect it from userland. Now we detected from userland that we won the race. So now it's stuck into this trap enlistment, and now we will basically overwrite structures in the resource manager to build a read primitive. And each time we want to increment an address, we are basically going to have to read the address in the first place. But to read the address, we have to increment it in the first place. So it takes a little bit of time, actually. And yeah, so here we're reading the different addresses on the processes to find the system process. So we found the system process, and our system. So the last thing I want to show is, as well, we actually implemented the previous mode primitive, which works as well on Windows 10 64-bit. So now our exploit actually use this method for 64-bit 10 because it's never going to crash. So the race is the same, but it's just once we won the race, the parsing of all the structures, we can just read and write arbitrary memory, so just right away. So it's a lot faster. Okay, as you can see. So what we can get from that, it was very reliable, exploitable race condition. The increments make it a little bit less reliable because of the fact that we overwrite a pointer. But if you actually use a CFG bypass or actually to get code exec in the kernel, we may not have this problem. It was very interesting for us from a research point of view to actually see after the fact that that the approach they took was different, and it was valuable. We'll publish more details about the in like a 5-blog post series, so if you're interested. And yeah, that's all for me. If you have any question. Yeah, go for it.
Thanks a lot for your talk. When you spoke about Heap spraying, you showed that you create 2 pair of pipes, right? And I didn't understand why did you receive these messages on one pipe to create holes. Can you elaborate on?
So the technique is a little bit funky, but the idea is that the allocation is not about creating a pipe, but it's about when you actually write data on the pipe. So the idea is we create pipe A and B, and we once we have created both pipe, we send data on one pipe and the other, one pipe and the other. And so the strategy with Feng Shui is to make a layout that creates hole. So what you don't understand is why we create hole. So we create hole because we want the enlistment to be stuck between other allocation. That's the Feng Shui technique. If you look online.
I thought it is for buffer overflow on the heap, right?
No. So here, the idea is not to overflow adjacent chunks. It works as well for overflowing adjacent chunks. You can use similar techniques. But here, really, the technique is that later, if we are here and our free chunk is not stuck in between other chunks, what happens is the memory allocator will coalesce this chunk in red with other thing, and then we have no idea of the size of the chunk to replace, and we want to know the size.
Thank you, now I see.
Yeah.
Are there more questions?
Thank you. I'll be around anyway, if you have any questions.
Then thank you for the amazing talk.
Thank you.